Gabon, equatorial Africa, a land of forests, rugged hills, and lush river valleys. For more than 1 billion years, the rocks here held important clues to a question that would not be asked until man entered the nuclear age. In the midst of the jungle is the Oklo site, a rich deposit of uranium. 2 billion years ago, it was even richer, concentrated enough for a natural chain reaction to start. This ancient, natural nuclear reactor released an estimated 100 billion kilowatt hours of energy over a period of 500,000 years. In the process, it produced radioactive waste. Waste identical to that produced by nuclear power generation today. The waste created there was immobilized in the immediate vicinity of the rock until it decayed to harmless levels. It remained unknown until man came here in search of uranium. What happened to that waste, how it reacted with the rock, and how far it moved are important clues offered by Oklo. Clues to the question of how man can isolate the nuclear waste he has produced.
We've learned to harness nuclear energy. I can't understand why we can't do anything with the waste of it.
I know that it is a problem and that there's nobody that's real super secure about what is being done with nuclear waste, and that it's something that there needs to be some technological improvements on it.
I am a supporter of nuclear energy as a, source of energy for the future, but on the other hand, I don't know what to do with the nuclear waste because I think there is very little known about them.
Well, right now I wouldn't build any more nuclear plants, and I wouldn't certify any more plants to open up until, to me, that's the major problem, getting rid of the waste.
I don't even know whether there's a problem that exists. That's how little I know about it.
Of course it's dangerous. Any of those things, because they can be uncovered, are dangerous. There has to be some way where it can be neutralized. I know about half-lives, and I know that these things will go on for 20 or 30,000 years. But I tell you, it can't be any worse than them dumping toxic chemical waste into the ocean or around.
What they're working on has got some way to dispose of that nuclear waste, bury it. It's still as dangerous even if they bury it, isn't it? So I don't know.
I think it can be solved. I think it has to be solved.
Well, I think we should do something about it ourselves. I mean, now. I don't think you should wait. You're going to have to do it now.
Any discussion of nuclear waste raises scientific and technical issues, political issues, and yes, emotional issues. Above all of this stands a basic fact. Mankind has produced a measurable quantity of nuclear waste that exists right now. In dealing with this waste, there are 2 roads we can pursue. The first is to continue what we've done in the past, to store the waste safely, contain it, and manage it. This places a burden on future generations. They would have the caretaking responsibility for waste that we have produced. The second road leads to the development of a safe, permanent disposal system that will isolate nuclear waste from man's environment, a system that will not require caretaking by future generations. This film is a progress report on the journey down that second road. We will see what has been accomplished and what is currently being done by the U.S. Department of Energy's National Waste Terminal Storage Program. This is a nuclear power plant west of Chicago. The reactor itself is just below these reinforced concrete shields. Now, inside the reactor are hundreds of fuel assemblies containing thousands of pellets of enriched uranium. These uranium pellets, before they go into the reactor, are not particularly radioactive. I could hold them in my hand with no ill effects. But when they come out of the reactor, well, that's another story. Inside the reactor, there's a fission reaction, the splitting of uranium atoms. In the process, heat is generated and used to make steam to run turbines for electrical power. But the reaction also creates nuclear waste. When the uranium atoms are split, over 200 different materials are created. These are called fission products. Other so-called heavy elements, like plutonium, are also created in the process. Fission products and heavy elements pose distinctly different problems based on the strength of their radiation and the length of time they remain radioactive. Fission products, like varieties of cesium and strontium, are at first extremely radioactive. They produce penetrating radiation and require heavy shielding to protect anyone nearby. But because they emit large quantities of strong radiation, they give up their energy rapidly and lose their tendency to produce radiation relatively quickly. The opposite is true of the heavy or transuranic elements like plutonium. They are less radioactive and produce radiation that is not penetrating, but they remain radioactive for a very long time. The radiation from plutonium, for example, is hazardous only under certain conditions. It must be ingested or inhaled in order to pose the great hazard usually attributed to it.
Now, these fission products aren't floating around the reactor. They're bound up in the structure of the uranium pellets inside the fuel assembly. But the fission products do gradually slow the reaction down. The reactor loses its efficiency and its ability to produce power. So these spent fuel assemblies are replaced periodically with fresh ones.
The spent fuel assemblies, now radioactive, are pulled from the reactor and moved to temporary storage pools next to the reactor. The entire procedure is carried out underwater to protect the operators from radiation. When the spent fuel is removed, only 5 pounds of every 100 pounds of uranium have been consumed in the nuclear reaction. Of that 5 pounds, about 3.5 were turned into fission products and 1.5 into heavy elements like plutonium.
Spent fuel could be stored like this for an extended time, but this was never intended to be a permanent disposal method. And many reactors are simply running out of space. All of the spent fuel produced in the past 20 years could be stored in a pool just 90 by 140 feet. By the year 2000, the industry might need a dozen pools of that size. Before permanent disposal facilities are developed, interim storage of spent fuel may require additional pools similar to this one, pools that are located away from existing reactor sites. But this spent fuel represents only one part of America's nuclear waste problem.
This is the Hanford Reservation. In the 1940s and 50s, 9 nuclear reactors were built here along the Columbia River. Their purpose was to produce plutonium for nuclear weapons. To extract the plutonium, spent fuel from these reactors was dissolved in acid. The resulting liquid waste contained dissolved or suspended fission products.
Millions of gallons of highly radioactive liquids have been produced right here at the U.S. government's Hanford Reservation in Washington State, as well as other government facilities. This is a tank farm, and below ground here are double-wall steel tanks, each containing about 1 million gallons of waste. But these tanks, along with expanded storage of spent reactor fuel, do not offer long-term solutions to the problem of nuclear waste. Regardless of the origin of high-level or highly radioactive nuclear waste, whether it is from commercial power reactors, weapons production, or from the reactors of nuclear-powered naval ships, we need a disposal method that can totally isolate it from our environment. There is a well-developed concept for accomplishing this, a concept that has been endorsed by a great number of scientists and engineers, including the National Academy of Science and many other professional groups. A concept that is backed by impressive evidence accumulated in the laboratory and in the field. The concept is this: isolation of the waste in deep underground repositories, similar to a large mine. Such a repository will use a series of natural and man-made obstacles or barriers to keep nuclear waste away from man and his environment. Man-made barriers will be designed to provide complete containment of the waste for at least several hundred years. During this time, the waste loses nearly all of its heat and most of its radioactivity. Natural barriers provided by the geologic formation and overlying strata will protect the man-made barriers and confine any remaining long-lived radioactive materials to the immediate underground area of the repository for at least 10,000 years.
The first set of barriers will be provided by the waste package. The waste itself will be a durable solid, something that will not easily dissolve or otherwise degrade. This solid waste form, buried deep, might be sufficient in itself to isolate the wastes. But in addition, this waste form will be sealed in special canisters. The canisters, in turn, will be surrounded by an overpack material. All of this will be placed in sleeves, lining holes bored in the repository chamber floor. The sleeves will then be surrounded by special backfill. This backfill provides a sorptive layer that limits corrosion and impedes any movement of groundwater to or from the waste package. This entire waste package will be located within a geologic system especially chosen to provide an additional set of barriers. The host rock will contain the waste packages. This will be a solid rock formation that has remained stable for at least several million years. The rock will also be resistant to penetration by groundwater. The repository chambers will be backfilled and all access shafts will be carefully plugged. Strata over and around the repository can provide isolation from groundwater sources that could reach the surface. The sheer depth of the repository, approximately 2,500 feet, provides another barrier. Each of these individual barriers should be able to isolate nuclear waste for the necessary period of time. But the use of conservative design and multiple barriers creates a redundant system that multiplies our confidence that the waste will remain isolated.
The idea of disposing of nuclear waste in repositories deep underground is not a new one. As early as 1957, scientists were recommending that we investigate stable rock formations as possible sites for isolating waste. The first geologic material explored, and the one we've researched the most, is this: rock salt. Today, a number of geologic materials, in addition to salt, are being investigated for potential repository use. Researchers are investigating granite and related types of rock, sedimentary deposits like shale, and volcanic rocks like tuff and basalt. Regardless of the type of rock, to be an effective part of the multiple barrier system, it must be stable. It's a fairly simple task for geologists to identify stable rock formations and make reliable predictions about their continued stability. But they also need to know what effect, if any, the waste package might have on the rock. This cavern is 550 feet below ground in a Louisiana salt mine. Because nuclear waste generates some heat, tests are being conducted to see what that heat does to the salt. In this case, electric heaters have been installed in holes bored into the salt. These heaters simulate the heat of the waste package. Instruments around the heater are used to determine how rapidly and how far the heat travels, whether the salt moves, and other data.
Halfway across the country in Washington State, similar tests are being conducted in basalt, a type of volcanic rock. This is the near-surface test facility, a series of tunnels bored into the side of Gable Mountain. Again, electrical heaters and careful instrumentation are being used to determine the effects of a simulated waste package on the rock.
Well, we're standing at the site of the first full-scale heater tests within the near-surface test facility of the basalt project, and in front of me we have a heater which is designed to heat a surrounding rock area. It is surrounded by 8 peripheral heaters which will simulate the heat coming from surrounding waste canisters of nuclear materials. And the idea here is to look at the stresses imposed on the rock by the heat coming from the heaters in this area. This test is part of the overall program to see whether tunnels in basalt, such as the one we have here, can withstand the thermal stresses of a nuclear waste repository.
In addition to the effects of heating, we need to determine if the radiation from a waste package will in any way affect the rock. This chamber inside Gable Mountain will house some of these experiments. Several test packages of radioactive waste will be lowered into holes that have been drilled into the floor. About 800 miles south of here, at the government's Nevada test site, there's an experimental test facility that has been mined in a granite formation. Canisters containing spent fuel from nuclear reactors have been placed in boreholes in a tunnel 1,400 feet beneath the surface. Electric heaters are being used in other holes to determine the effects of heat alone versus heat and radiation. The spent fuel and the heaters will be left in place for a period of 3 to 5 years. The results of these tests will then be compared to computer predictions of what should happen. All of these field activities are designed to test and evaluate the rock in which nuclear waste might be placed. But equally important are investigations of groundwater systems around the repository. All around the repository level are layers of different types of rock. Strata, like you see exposed here. Some of these layers contain groundwater. Others are quite dry and actually impede the flow of water. Now, when geologists refer to groundwater, they're not talking about great underground rivers flowing freely. Groundwater occurs in layers of porous rock, something like a sponge. When water flows through it, the rock acts like a filter. Now, some underground environments are better than others in terms of their ability to filter any waste that might get into the water. It's important to find these areas because water provides the only realistic potential for transporting waste from deep in the repository to the surface environment.
To help geologists and hydrologists evaluate the effectiveness of the entire geologic system for repository use, extensive drilling, coring, and other tests are conducted. This kind of investigation is currently being conducted in Washington State, Nevada, Utah, 3 of the Gulf Coast states, and may soon be started in other states. For example, in Louisiana, 2 salt domes are being evaluated.
In the Gulf Coast, we have what are termed recharge areas where rainwater seeps into the formation and slowly percolates through the formation. It flows downslope past the dome, and I might add that the dome, even with this water flowing past it, has existed here for about 150 million years. The water continues downslope and out under the Gulf Coast. This is a very slow process. It may take from the time of entering the aquifer to out under the Gulf Coast hundreds of thousands of years for this water to make that trip. The drilling is to determine in and around the dome the rate of flow and the amount of water that are present in some of these upper aquifers toward the upper portion of the dome where the repository would be located. We need the flow rates and the properties of the formations to use in the performance assessment models so we can predict the behavior of the repository, say, over the next 100,000 years.
And what we are doing right now is a pump test. And at this pump test, we're measuring the physical parameters of the formation that we're testing. Primarily what we're doing is we are pumping water at a known volume from the formation and seeing how it responds. From this response, we are able to tell things like whether there are any connections between this formation and another formation at the site, and how fast the water is traveling through the formation at this location. We need to know this primarily because it gives us an indication of where and how soon any contamination from any dome that we use as a repository, how long it would take for the water to get back to the biosphere, back to the Earth, the surface.
Conservative design of a repository demands that we plan a system that will continue to isolate waste under the worst possible circumstances. That would occur if all of the multiple barriers provided by the waste form and the waste package were somehow breached, and at the same time, groundwater entered the repository. The chances of this happening are extremely slight. But even if it did occur, research being done here at the Argonne National Laboratory indicates that the geologic system would continue to isolate the waste.
In our lab, our main objective is to determine the ultimate safety of a nuclear or radionuclide repository, a repository for reactor wastes. We do this by trying to determine the worst possible case, the case in which the material would be released from its source and getting into the groundwater. And we try to measure the uptake of the radioactive wastes that might be carried in groundwater by the surrounding rocks in the aquifer. If this uptake can be shown to be virtually complete, we believe that this is a measure of the safety of the repository, because if the uptake is complete, by the time any hazardous material would get out of the repository, it would have decayed away. Our particular test is taking a sample of rock and forcing solutions of radioactive material through this basalt. The radioactive material in this case is plutonium, and we measure the amount of plutonium that goes into it, and we measure the amount of plutonium that comes out. Our measurements show that the retardation of the rate of migration of the nuclide is very great, and that calculations show that for any reasonable travel, plutonium would long since have decayed away before it would get into the environment.
We are gradually confirming, through both laboratory and full-scale field testing, that the many barriers provided by the geologic system alone can successfully isolate nuclear waste. But before the geology ever comes into play, there are the barriers offered by the waste form and the waste package. Liquid wastes will have to be solidified before disposal. For several years now, researchers at Battelle Northwest Laboratories and others have been developing techniques for doing this.
Vitrification is a process where we convert liquid nuclear waste to a stable, solid glass form. Simply, the process is we take the liquid waste and we dry it in a furnace that we call a calciner. This dried powder is then mixed with crushed glass. The glass and waste powder melt together and form a solid black glass. The reason we convert liquid waste to a glass is a very stable form, very leach resistant, so it can be stored for many thousands of years in a geologic repository. In addition to glass, we're also looking at other solid forms, such as synthetic rocks. The reason is some of these new waste forms have the potential for being more durable, and we're investigating these to evaluate their potential as far as waste disposal.
All of these laboratory tests and field activities are part of a national program to develop a geologic waste repository. Every core sample, every laboratory test is changing conjecture, theory, and prediction to established fact. Large-scale field tests are proving theories in the real world. We are gathering an extensive base of information about all elements of the multiple barrier geologic system, and yet questions remain because of the incredibly long time periods over which a repository must function. Like every other element in the design of the repository, these uncertainties are planned for. When we cannot predict with absolute certainty, we over-engineer and overbuild. Instead of one or two barriers, we use a system that provides multiple barriers and sub-barriers to contain nuclear waste.
The knowledge we have gained clearly indicates we can build a geologic repository that will provide maximum long-term security. Whatever the location, detailed and time-consuming on-site studies will be conducted in order to thoroughly evaluate the geologic system for waste disposal. The repository itself will be developed in a careful, step-by-step approach. The information gained in each step will be carefully evaluated and studied before going on to the next. By proceeding in this prudent, careful fashion, we will be able to dispose of our own nuclear waste. We can take responsibility and not defer the problem to future generations. We can use the Earth, the geologic systems it provides, and our own engineered barriers to safely isolate our most hazardous nuclear wastes.